You think water is simple, clear, passive, obedient. You imagine it as the most ordinary thing in the universe. 2 atoms of hydrogen, 1 atom of oxygen, nothing mysterious. You are wrong. Water does things matter is not supposed to do. It expands when it freezes. It climbs walls. It refuses to behave like a normal liquid. You were taught rules about physics, rules about temperature, rules about density, rules about how molecules should move. Water breaks them, quietly, constantly. And the disturbing part is not that water is strange. The disturbing part is that physicists still struggle to explain why something so simple behaves so impossibly. You look at a glass of water and see something familiar. Physics looks at it and sees a problem, a deep one, a dangerous one that forces us to question what we think we understand about matter itself. You were told that simplicity in structure leads to simplicity in behavior. A chair is complicated. A computer is complicated. But a molecule made of 3 atoms should not be complicated. That is the intuition. Physics itself encourages this way of thinking. Break things into smaller parts. Understand the parts. Predict the whole. This works beautifully until you meet water, because water should be easy. 2 hydrogen atoms, 1 oxygen atom, a small angle between them, a neat, tidy structure you could draw with a pencil. If the rules of matter were straightforward, water would behave like the simplest liquid imaginable. It would flow. It would compress when cooled. It would solidify into a tighter structure when frozen. Its properties would be predictable from its ingredients. But the moment you look closely, the expectation collapses. Water is not normal. Most liquids become steadily denser as they cool. Water does not. Most substances contract into orderly solids. Water expands. Most simple molecules produce simple phase behavior. Water produces dozens of strange forms of ice, each with different internal arrangements. And this is not a small deviation. This is not a minor exception. Water violates the pattern entirely. Imagine being a physicist encountering this for the first time. You're given the molecular structure, just 3 atoms. You apply the standard tools of thermodynamics and statistical mechanics. You expect straightforward answers. Instead, you find anomalies everywhere. Its boiling point is far too high for such a light molecule. Its surface tension is unusually strong. Its heat capacity is enormous. Its liquid form persists under conditions where similar molecules would already be gas. Every measurement quietly refuses your expectations. So the question begins to change. The puzzle is no longer, what is water made of? That part is simple. The real question becomes something more unsettling. Why does something so structurally simple produce behavior so difficult to predict? This tension exposes a hidden assumption you rarely question, the idea that understanding components means understanding reality. Water is the first warning that this assumption may be wrong, because nothing about a single water molecule tells you what billions of them will do together. Nothing in the diagram explains the liquid in your glass. Nothing in the structure predicts the substance that shapes climates, erodes mountains, or sustains living systems. The ordinary appearance is misleading. The transparency is misleading. The familiarity is misleading. You think you understand water because you see it every day. But physics approaches it with hesitation, because beneath the simplest molecular design lies behavior that refuses simple explanation. And the deeper you look, the more the rules you trust begin to bend. You carry a simple rule about matter. Cool something down, and its particles slow. Slower particles move closer together. Closer together means greater density. Cold compresses. Heat expands. This feels obvious because it is almost always true. Metals contract when cooled. Gases shrink dramatically. Liquids become more compact as temperature drops. Nature appears consistent, predictable, obedient to this pattern. Then water approaches freezing, and the rule breaks. As liquid water cools, it does become denser, but only to a point. At about 4 degrees Celsius, something strange happens. The trend stops. Further cooling makes water expand, not when it freezes, before it freezes. By the time water becomes ice, its volume has increased by about 9%. Its molecules spread apart. The solid is less dense than the liquid. Ice floats. You learned this early. You accept it without discomfort. But physics does not accept it so easily, because floating ice is not a trivial detail. It is a direct violation of how matter should organize itself. A solid is supposed to be a tighter arrangement than a liquid. Cooling removes motion. Less motion should allow particles to pack closer. This is what happens in nearly every known substance, except water. To understand why this is disturbing, imagine you knew nothing about water, only the general rules of matter. You would confidently predict that frozen water should sink, oceans should freeze from the bottom upward, lakes should solidify into dense blocks. Reality does the opposite. The coldest, most ordered form rises to the top. This reversal suggests something deeper than a simple exception. It suggests that the internal organization of water is not governed by the same priorities as ordinary matter. Instead of packing as tightly as possible, water's molecules arrange themselves into an open structure when frozen, a rigid framework with empty space inside it, a solid built around gaps, a solid that deliberately wastes space. This is deeply unnatural. Matter normally seeks efficiency. Lower energy usually means tighter packing. But water's lowest energy arrangement is strangely spacious. Even more unsettling, this tendency begins in the liquid itself. Liquid water is not a random swarm of independent molecules. Even before freezing, it carries traces of this open structure, fragments of order constantly forming and dissolving. The liquid already contains the blueprint of the solid. So the boundary between liquid and ice is not a clean transition from disorder to order. It is a shift in the balance of structures that were already present. This blurs another intuition, that phases of matter are fundamentally different states. In water, the difference is subtle, unstable, almost ambiguous. But the density paradox carries consequences far beyond physics laboratories, because ice floats, lakes freeze from the surface downward. A layer of ice insulates the water below, allowing life to survive winter. Global ocean circulation depends on these density changes. Earth's climate stability is shaped by this single anomaly. An entire planetary environment depends on matter behaving incorrectly. So now the puzzle deepens. Water is not merely complicated, its most basic behavior contradicts the simple logic of temperature and motion. And the explanation cannot come from looking at individual molecules alone. Something else is happening, something relational, collective, structural, something hidden in how water molecules influence one another. To understand why matter would prefer empty space over tight packing, you must abandon the picture of isolated particles entirely. You must begin to think about connections. You imagine molecules as tiny objects, little spheres, solid pieces of matter. They collide, bounce, separate. This picture is comfortable, it is clean, it is wrong, especially for water, because water molecules do not simply move past one another. They attach, they release, they reattach constantly. Each water molecule carries a subtle imbalance of electric charge. The oxygen side pulls slightly negative. The hydrogen side remains slightly positive. This difference is small, almost insignificant, and yet it changes everything. Nearby molecules feel this imbalance. Positive regions are drawn toward negative ones. A temporary attraction forms. Not a full chemical bond, but not mere proximity either. A connection, a hydrogen bond. If water behaved like a simple liquid, these attractions would be weak disturbances, minor corrections to otherwise independent motion, but they are not. Every molecule forms several of these bonds at once. A vast network emerges, a shifting architecture where each molecule is linked to its neighbors in a constantly rearranging web. And the key word is constantly. These bonds form and break trillions of times per second. The structure never settles, the architecture never finishes. Water is a structure that refuses permanence. Imagine a building where the walls rebuild themselves every instant, where every connection dissolves as soon as it forms, where stability emerges from endless instability. That is liquid water. The comfortable picture of isolated particles moving randomly must now be abandoned. A single molecule cannot behave freely. It is constrained by its neighbors, which are constrained by their neighbors in an endless chain of influence. Motion becomes cooperation. Behavior becomes collective. This network explains the strange openness of ice. When water freezes, these temporary connections lock into a stable geometric pattern, a rigid framework shaped by the directional pull of hydrogen bonds. The molecules cannot pack tightly because the bonds demand specific angles and distances. Structure wins over efficiency. But the deeper consequence is more unsettling. If water's properties arise from this vast fluctuating network, then no single molecule contains the explanation for the liquid's behavior. The essential physics is not in the parts themselves, it is in their relationships. This challenges a powerful intuition about science. You assume that if you understand each component perfectly, the whole system becomes predictable. This reductionist promise feels fundamental to physics. Water resists this promise. Even with precise knowledge of individual molecules and their forces, predicting the behavior of billions interacting simultaneously becomes overwhelmingly complex. The network has too many possibilities, too many configurations, too many interactions unfolding at once. Order emerges from chaos, but the chaos never disappears, and something even stranger follows. At any moment, liquid water contains fleeting patterns resembling ice, tiny regions of temporary order, while solid ice still contains vibrations and disruptions resembling liquid motion. The distinction between states becomes blurred because the underlying network never truly stops changing. So the picture shifts again. Water is not a substance made of stable objects. It is a dynamic system of relationships, a choreography of connections that exist only briefly yet shape everything. And once you accept that matter can behave this way, as an ever-changing network rather than a collection of things, another assumption begins to weaken. The assumption that matter has clearly defined states at all. You were taught that matter has categories: solid, liquid, gas, clear boundaries, clean transitions. One state becomes another at precise conditions. Heat ice and it melts. Heat water and it boils. Each phase has its identity. Each identity is stable. This classification feels fundamental, as if reality itself respects these divisions. Water does not, because water can exist in states that refuse these categories. Take supercooled water. Liquid water can be cooled well below its normal freezing point and still remain liquid, perfectly fluid, perfectly mobile. No ice. All the conditions for freezing are present. The temperature is low enough. The molecular motion is slow enough, and yet nothing happens. The liquid waits. A tiny disturbance, a vibration, a particle of dust, and the entire structure suddenly reorganizes. The water crystallizes almost instantly, as if it had been frozen all along, but had simply refused to admit it. The boundary between liquid and solid was never definite. It was conditional, fragile, or consider superheated water. Under certain conditions, water can remain liquid even above its boiling point. It does not form bubbles. It does not transition to gas until suddenly it does, violently. Again, the state of matter is not determined solely by temperature or pressure. It depends on subtle details, hidden conditions, microscopic events. The categories blur. Even more unsettling, physicists suspect that water may exist in multiple distinct liquid forms, different internal organizations of the same substance, separated by subtle structural transitions. Liquid becoming another liquid, same molecules, same temperature range, different internal order. A phase of matter that looks identical from the outside, but is fundamentally different within. The familiar chart of states, solid, liquid, gas, begins to look less like a law of nature and more like a rough summary, a simplified map drawn over a much stranger terrain. And water continues to complicate the picture. Near its critical point, where the distinction between liquid and gas disappears, water becomes a single continuous phase with properties of both. Density fluctuates wildly. The boundary between states dissolves entirely. Liquid and gas stop being meaningful distinctions. Reality offers no sharp edge. What you called states of matter are revealed as convenient descriptions of typical behavior, not rigid identities. Water exposes this limitation. Its molecules are constantly rearranging through hydrogen bonds, constantly forming temporary structures, constantly shifting between order and disorder. In such a system, fixed categories become unstable. Matter does not always choose a state. It hesitates. It fluctuates. It occupies possibilities rather than definitions. This challenges another quiet belief that nature operates through clear classifications that we simply discover. Instead, the categories may come from us, from our need for simplicity, from our preference for stable labels applied to unstable reality. Water behaves not as a set of distinct phases, but as a continuous spectrum of arrangements, some stable, some temporary, some barely defined. And if the identity of matter depends on vast networks of interacting molecules, and if those networks never settle completely, then a deeper realization emerges. What matters most is not what individual molecules are. It is what many molecules do together. The behavior of water is not contained in its components. It emerges from their cooperation, and this raises a troubling possibility. Perhaps the rules governing large systems cannot be reduced to simple rules about small parts. You were taught a powerful promise about science. If you know the rules governing the smallest pieces of reality, you can explain everything built from them. Understand atoms, and you understand matter. Understand molecules, and you understand substances. The whole is just the sum of its parts. This idea is called reductionism. It is one of the deepest assumptions in physics. And for many systems, it works remarkably well. But water reveals a limit, because knowing a single water molecule does not tell you what liquid water will do. Knowing two does not help much either. Even knowing thousands changes very little. The essential behavior appears only when vast numbers interact together. Millions, billions, trillions. At that scale, something new emerges. Physicists call this emergence. When a system displays behavior that cannot be understood simply by studying its components in isolation. Temperature itself is an example. A single molecule has no temperature. Pressure does not exist for an individual particle. These properties appear only in large groups. Water pushes this idea to an extreme. Its density anomaly, its high heat capacity, its unusual surface tension. These are not properties of individual molecules. They are properties of the collective network formed by countless interactions. The hydrogen bonds you encountered earlier are simple in isolation, but when billions of molecules form and break these connections simultaneously, the possibilities explode. Each molecule influences several neighbors. Those neighbors influence others. Changes ripple through the system. The result is a many-body problem, one of the most difficult challenges in physics, because predicting the behavior of such a system requires tracking an astronomical number of interacting relationships, not a few variables, not a manageable set of equations, an overwhelming web of mutual influence. Even with modern computation, simulating liquid water accurately remains extraordinarily difficult. The system is too rich, too sensitive, too interconnected. The rules at the small scale are known, yet the large-scale behavior remains elusive. This exposes a disturbing truth. The idea that reality is fully understandable by breaking it into pieces may itself be incomplete. The pieces alone are not enough. Relationships matter. Collective behavior matters. Scale changes the nature of explanation. When enough components gather, new rules appear, not because the old rules are violated, but because their consequences become unpredictable. More becomes different. Water is a clear demonstration of this transformation. Its familiar properties arise from cooperation across unimaginable numbers of molecules, none of which contain the full explanation. And this forces a shift in perspective. You no longer ask, what is a water molecule? You must ask, what does a vast community of water molecules become? The substance in your glass is not merely a collection of identical units. It is a dynamic society, endlessly negotiating structure, constantly reorganizing itself, generating behavior that no individual member intends. Reality at this scale is not built from objects. It is built from interactions. And once you accept this, another unsettling question emerges. If even simple matter depends on overwhelming complexity and collective effects, what does it mean to say we truly understand it? You assume that physics explains things. That is its purpose, to reveal causes, to expose mechanisms, to replace mystery with understanding. And in one sense, physics explains water extremely well. We can measure its properties with astonishing precision. We can predict how it flows through pipes, how it freezes in clouds, how it absorbs heat in oceans. We can model its molecular interactions using quantum mechanics. We can simulate small collections of molecules on powerful computers. The predictions work. The equations work. And yet something remains unsettled, because prediction is not the same as understanding. Physicists can describe the forces between water molecules with great accuracy. They know how electric charges interact. They understand the geometry of hydrogen bonding. They can calculate probabilities for different molecular arrangements. But when these rules are applied to vast numbers of molecules, the explanation becomes indirect. We do not derive water's strange behavior from first principles in a simple, transparent way. We approximate, we simulate, we adjust models until they match observation. We describe what happens without fully grasping why the collective outcome takes the form it does. The difference is subtle but profound. Imagine predicting the motion of a storm. You may forecast its path accurately using complex calculations, yet still struggle to explain why its structure takes a particular shape. Water presents a similar challenge. Its anomalies emerge from countless interactions governed by quantum mechanics, the most fundamental theory we possess. But the connection between those microscopic rules and the macroscopic behavior of water remains difficult to trace in a clear, intuitive chain. The explanation exists, but it resists simplicity, and this reveals a quiet boundary in scientific knowledge. Physics often provides models that work rather than explanations that satisfy intuition. It offers mathematical descriptions that predict outcomes, even when the deeper conceptual picture remains obscure. We know the rules, we know the ingredients, yet the full story of how those rules produce the familiar liquid in your glass is still unfolding. This is not failure. It is a recognition of complexity. Nature may not organize itself in ways that allow complete human comprehension. The demand for simple explanations may be a human preference rather than a property of reality. Water, the most common substance on Earth, exposes this tension. Something so ordinary reveals the limits of our explanatory power. A substance you drink every day still challenges the deepest theories of matter, and this realization forces a final shift in perspective. Perhaps the laws of physics are not rigid commandments that dictate simple behavior. Perhaps they are constraints within which reality explores possibilities, producing outcomes that remain richer than our explanations. Water does not merely challenge specific rules. It challenges the idea that reality must conform to our expectations of clarity. And if even the simplest substance reveals such depth, such resistance, such mystery, what does that say about the nature of reality itself? You began with a simple belief. The universe follows rules. Matter obeys them. And with enough effort, those rules become understandable. Water quietly unsettles this belief, not because it breaks the laws of physics, but because it reveals how incomplete our intuition about those laws truly is. You expected matter to behave efficiently. Water prefers spacious structures. You expected colder to mean denser. Water expands. You expected clear states of matter. Water hesitates between them. You expected simple parts to produce simple behavior. Water produces endless complexity. At every step, the problem was not the universe. The problem was the picture in your mind. Physics does not promise that reality will be intuitive. It does not promise that nature will organize itself according to human expectations of simplicity or clarity. It only describes what happens, and what happens, even in a glass of water, is stranger than the rules you thought governed it. This reveals something profound about physical law. Laws are not instructions that dictate obvious outcomes. They are constraints, boundaries within which enormous possibilities unfold. From simple equations emerge structures, behaviors, and patterns that no simple intuition can anticipate. The universe is not obligated to be understandable in the way you prefer. It is not built from tidy categories. It is not arranged for conceptual comfort. Water makes this visible because it is so familiar. You encounter it daily. You trust it. You believe you know what it is. Yet beneath its transparency lies a reality defined by unstable networks, collective behavior, blurred identities, and explanations that remain incomplete. The ordinary world is not ordinary at all, and this may be the most unsettling lesson. The deepest mysteries of physics are not always hidden in distant galaxies or exotic particles. Sometimes they sit quietly on your table, revealing that the fabric of reality is richer and less obedient than the stories we tell about it. Water does not break the rules of physics. It reveals that the rules were never the full story. And if something as simple as 3 atoms can generate such depth, such unpredictability, such resistance to complete explanation, then the universe you inhabit is not a machine you fully grasp. It is a process you participate in, a structure still unfolding, a reality whose simplest elements already exceed the limits of intuition. You look at water and see something familiar. Physics looks at it and sees the edge of understanding.